Good afternoon. Thank you for coming. And also thank the organizer for hosting this very nice symposium. My name is Jing, and I'm from the Institute of Material Research and Engineering. Today I would like to share our result on the anomalous thermoelectric transport in Mos2 flexible bore nitric heterostructure. Firstly, I will give a very brief introduction about thermoelectrics. The story of thermoelectrics actually begins at 1821. When Thomas Johann Seebeck found that when we apply temperature gradients along materials, it will also create a voltage drop in the materials. And at the microscopic level, the charge carriers will diffuse it from the hot side to the cold side, driven by this temperature gradient. And also the chemical potential of the charge carriers will also modified by this temperature gradient. So you can create this kind of electrical potential along the materials. And moreover, he found that the open circuit voltage induced by this temperature gradient is actually proportional to the temperature difference among them, which is defined as the Seebeck Coefficient. You see here. And the thermoelectrics attracted a lot of attention due to its ability to direct convert the heat energy into electrical energy. So it's seen as the alternative of the sustainable energy resources, because it's like the heat energy is all over the world. It's like the geothermal or the waste heat in the car engine. We can even make use of our body heat. So typically thermoelectric devices actually combined with two types of material. One is the N-type material and another is P-type materials. In N-type materials, the charge carriers is the electron. So when you apply temperature gradient, the electron will diffuse it from the hot side to the cold side. So it will give you a negative Seebeck coefficient. And for the same reason for P-type materials, because the charge carrier is the host, so you will have a positive, normally you will have positive Seebeck coefficient. So by combining with the P-type material and N-type material, you can actually build this closed circuit current for the thermoelectric device applications. So it's like for N-type materials, you have the electrical current flow from the cold side to the hot side. So for the P-type pillar, you have the current from the hot side to the cold side. So by this closed circle current flow driven by the heat, you can pump the heat energy and convert it into the electrical energy. And for the vice versa, you can also apply a power supply here to make a refrigeration by using the thermoelectric devices. So when you're talking about the applications, the efficiency is people concerned. The efficiency of thermoelectric devices depend on this ZT value, which called the figure of merit. And the S here is the Seebeck coefficient we talked in the previous slides, and the sigma is the electrical conductivity. T here is the absolute temperature. Kappa is the thermal conductivity. Basically, larger ZT give you higher efficiency. And here is the thermoelectric efficiency compared to the existing heat engines. And for the past decades, people is like making a lot of effort to increase the ZT value of thermoelectric devices. However, the commercial thermoelectric the ZT value of commercial thermoelectric devices is usually around 1, and it's much lower compared to the commercialized, much lower than the existing heat engine. This is because the anti-correlation between those parameters in the ZT values. And these pictures are shown in this picture. The x-axis here is the carrier concentrations, and when you increase the carrier concentrations in the materials, the electric conductivity will increase. However, at the same time, the Seebeck will drop. That means it's like where you have very high carrier concentration, it's like metals. The Seebeck coefficient is very small. It's around microvolt per Kelvin range. Although the Seebeck coefficient at the insulator is very big, it's like microvolt per Kelvin, but the low electrical conductivity actually avoid any charge current passed through the materials. So usually the good thermoelectric material is actually located at the semiconductors regions, which will both have relatively large Seebeck coefficient and also relatively large electrical conductivity. We call the here number is called the power factors. So you need to optimize the power factor for get very good thermoelectric performance. So from here we can find that actually the carrier concentration plays very important role to optimize the thermoelectric properties. However, you want to change the carrier concentration or the doping levels of bulk materials. It's not very easy. Because when you dopant, you should manually change the dopant's concentration. So when you do different doping level, you should prepare different samples. However, for two-dimensional materials, it's very easy to change the carrier concentration by the gate effect. Just apply simple like external electric field, and you can manually continuously change the carrier concentration within the two-dimensional materials. When we solve the linear Boltzmann transport equation under the relation time approximation, the Seebeck coefficient is given by this formula. Okay, the FFD here is the Fermi direct distribution, and the DE is the density of state. And the tau here is the energy-dependent reaction time. So we find people have proposed that in low-dimensional materials, the sharp change in the quantum confinement in the density of state will also increase the Seebeck coefficient. It's like for three-dimensional system, the density change is very smooth, but due to the quantum confinement and the low-dimensional system, you will have very sharp change in the density. This is all will give you the enhancement in the Seebeck coefficient. So based on those requirements, for 2D materials, we can easily play with the carrier concentration, and also the quantum confinement effects will also give you a strong effect enhanced in Seebeck coefficient. So we can find that actually 2D semiconductor is a very good platform to study the thermoelectric transport. So when we look back this formula, we can find actually there is another reaction time terms, because this is depend on different kind of scattering mechanism. Because for 2D crystal is also not like reflection, those impurities and the roughness and the surface will also affect this. So can we make use of this kind of effects? When we look at the first derivation of Fermi direct distribution, actually we find that only the charge carriers near the Fermi surface is actually contributing to the Seebeck coefficient. So when we have some special maybe defects or which can strong interaction with these charge carriers in the Fermi level, it will give huge impact in thermoelectric transport. For example, the magnetism or magnetic effects in materials. Actually, people have studied a lot to induce the magnetism in 2D materials. For example, people make like different heterostructure between the mode patterns. The lattice string will induce this periodical local magnetic field. And also the strong string induced by the bottom nanoparticles. The graphene on the bottom particles, the strong will give you very strong like a local magnetic field, which is up to 100 Tesla in this local. And also you can create like defects using like ion beam to create the defects on these 2D materials. And simply the vacancy also will give you the local magnetism in two-dimensional materials. However, to prove this, to prove the influence of those magnetism to the electrical transport is not that easy. Because 2D materials is actually extremely sensitive to the surface and the substrate due to its 2D nature. Those impurities on the surface or the roughness substrate will green up and will dominate the charge transport. So you cannot that easy to prove those effects. And here in 2D society, people will use oxygen-boron nitride. This is atomic bed. Another 2D material insulator to screen out the external disorder to make people to get approach to the intrinsic property of 2D materials. This is our typical device structure. We have few electrodes here. We use Mos2. It's like a well-studied 2D semiconductor. And we put this Mos2 plate on the hexagon nitride. And here is the nano-fabricated heater. So we use heater to pass it through the heating current. We create dual heating so we can have a local temperature gradient along these materials. And all these 2, 3, 4, 5 probe, we can probe performance for probe electrical conductivity to measure the electrical performance of these materials. And also this 4 probe measurement of this local is we fabricated nano thermometers. We can use these to define the temperature gradient of these materials. By this kind of structure, we can measure the thermoelectric transport of the two-dimensional materials. So we find actually when we get high temperature, the defects, this kind of defects is everywhere by using the scanning tunnel microscopy. It's everywhere. So, and also we can use by performing the STS scanning, we can get the band gap of this semiconducting Mos2. For purely Mos2, we know that it's not like direct band gap. So the conduction band minimum is actually located at this lambda point. And this subband structure can be reviewed by the resonant peaks by those STS spectrum. When we perform the STS at those defects region, we can find that those subbands actually give a large speed up to 50 millieV, which is strong evidence of the local magnetic state. So what will happen for the electric transport for those magnetic defects to the thermoelectric transport? Here we first perform the normal field effect transfer curve of this Mos2 Heterostructure heterostructure. When we apply gate voltage, positive gate voltage, we actually inject the electron into the materials. So the electroconductivity increase, so it shows very typical N-type FET behavior. It means electron actually is the charge carriers in Mos2 material, in these materials. We can find is a cross section here. This is for different temperature. You can see from here, the electrical conductance actually is increased when temperature increase. This is like typical metallic behavior. And for this bridge, it's like insulating or semiconducting. So we call this cross point is actually the metal insulated transition point. However, when it go to the lower temperature, when temperature is like smaller than T, we find this anomalous cross section here, which is like different from the cross section. And in order to make this more clear, we compare the sample with Mos2 hydrogen boron and Mos2 with normal sitting oxide. At high temperature, it's beyond 100 Kelvin. It actually shows the same behavior. You can see at the very high gate, it's like we're pushing the charge carrier into the conduction band, so it shows very metallic behavior. The conductivity actually decreases with increased temperature, which shows very clear metallic behavior. And for lower gate, it has insulating behavior. However, for Mos2 or hydrogen boron nitride sample at low temperature, it shows anomalous peak, which gives you a peak in the electrical conductivity, which is a hint of the strong correlation at low temperature. At high temperature, the transport is dominated by strong electron phonoscattering, which is also confirmed by the mobility, the temperature-dependent mobility behavior. And however, at low temperature, we can find like for Mos2 or hydrogen boron nitride, the mobility actually shows a peak in the low temperature, which is not found in the Mos2 silicon oxide sample. So when we look at the thermoelectric performance due to this magnetic vacancy, for Mos2 sample on high temperature, both samples shows negative Seebeck coefficient, which is because it's the N-type nature. And also, this is also confirmed by other previous results. However, at low temperature, the Mos2 or hydrogen boron nitride shows anomalous sign change in Seebeck. The Seebeck change from negative to the positive, while the electron while is still N-type material. That means which confirmed by previous result, which means the electrons is still the majority charge carriers. However, it shows positive Seebeck coefficient. And this sign change at low temperature is actually a signature of quantum lattice thermoelectric transport due to those magnetic impurities. When we look at the mod formulas previously, actually in metal and the degenerate semiconductors, the Seebeck coefficient is approximation by this mod formula. Here, the tau is the reaction time, the energy-dependent reaction. D is the density state. Dk is the group velocity. For this part, these two terms is actually the energy-dependent diffusive term, which is only the sign of this part is only depend on the charge carriers. That means for holes, you can only get positive Seebeck at this term, and the electrons will only give you negative. So the negative Seebeck for Mos2 is only coming from the scattering terms. So when you want to have a negative Seebeck coefficient, positive Seebeck coefficient for this term, it will only happen when the partially log tau divided by theta is smaller than 0. It's negative. So we also observe the same experiment, observe the same behavior for the positive Seebeck. We have the mobility actually increased with temperature, but for the negative Seebeck, the mobility is decreased with temperatures. And in compound-driven systems, the mobility is not as usual as which is proportional to tau. For in compound-driven system, the mobility is proportional to 1 divided by tau. So we can approximating the 1 divided by delta E as the 1 divided by kBT by temperature. So we can have this relationship where this term actually proportional to minus d mu b dt, which is consistent with what our experiment observation. This gives you quantitative explanation why you have the positive Seebeck coefficient in these low temperature regions. And the compound scattering in Seebeck coefficient actually can be described very well in these two bands history mode. Here, epsilon 0 is the distance between your magnetic band and the Fermi average. The count here is the bandwidth of your magnetic state. So the Sn can easily fit from the linear Boltzmann equation, and we can find it shows very nice fitting of our experiment data. Moreover, due to this strong scattering between the electron charge carriers and the quantum resonant peaks, we can have large enhanced power factor, 2 order of magnitude in the power factor for this Mos2 on hexagon boron nitride. And this lower here is the Zine chain position. And this is much larger than the previous reporting to the natural material. We have a quick summary. We demonstrate the vacancy in Mos2 can give you strong local magnetism. And also we demonstrate that this strong scattering due to the magnetic effect can give you the Zine change in Seebeck. And due to this strong scattering, we have give large enhancement in the thermoelectric transport performance. That's all. Thank you.
Any questions for Dr. Jing?
One question. So, why do we have all these vacancies in HPN?
HPN don't have vacancies.
No,
on
on the HPN substrate, but not on the silicon oxide.
On silicon also have, but
Also.
yeah, but because you can see the mobility change, right? For silicon side, actually the change is mainly screened by the impurity scattering, mainly saturation. However, for hexagon boron nitride, the mobility will decrease as temperature at the low temperature. Will decrease as temperature at the low temperature. It shows the peak here. Okay. You can see here.
This one is for HPN, right?
The bottom one is on silicon oxide. Because
okay.
you see, this saturation, that means at low temperature is dominated by the impurity scattering.
Okay.
Yeah. So then it's screened, and also the mobility actually is much smaller compared with the.
What about the Seebeck for Seebeck comparison? So in the HPN, there's a sign change.
Yes.
On silicon oxide,
You don't have, we didn't see. On silicon oxide, at high temperature, almost the same. At low temperature,
Okay.
you didn't see the sign change.
Okay. But for silicon oxide, even
Yeah.
for low temperature, there is no sign change.
Yes, yes.
Okay. Thank you.
Any more questions?
Okay, thank you.